And now,
Yes, it's okay. Please type F5 to see the full screen view.
I represent
Okay.
the Department of Aerospace Control Systems. And as you can see, there is no electricity in my district of Kiev. Sorry for this view. Paper outline, I am sorry. Processing information in the redundant inertial measuring instruments. Paper outline, motivation and state-of-the-art, objective of the research, mathematical background, main results, case study, conclusions. Motivation and state-of-the-art. One of the modern approaches to developing navigation instrumentation is the creation of complex navigation devices, which are close to inertial navigation systems by functional capabilities, but are characterized by lower cost and sizes. The successful implementation of this approach is achieved firstly by the appearance of high precision and miniaturized navigational measuring devices. Secondly, by the developing computing technique from the point of view of increasing memory capacity and speed of operation, and thirdly, by the developing electronics. The first circumstance makes it possible to include spatial position sensors and accelerometers in the navigation device and create a system capable of performing the functions of an inertial navigation system with less weight and dimensions, as well as using redundancy to increase the accuracy of these systems. The second circumstance makes it possible to implement rather complex algorithms for processing navigational information to increase the accuracy of the obtained data by algorithmic means. Objective of the research. Objective of the research is creation, improved algorithms of processing information in redundant inertial measuring instruments. There are several approaches to using redundancy in navigation measuring instruments. The most common method is the reservation of measuring navigation devices. To determine kinematic parameter projections onto the axis of the inertial reference frame is possible applying redundant measuring frames. This problem is of great importance for perspective measuring instruments as data about acceleration or angle rate onto the axis of the navigation reference frame is widely used in the loss of control of modern moving objects. Figure 1 represents the problem of determining kinematic parameters. Improvement of the system's reliability by the duplication of measuring devices axis is shown in Figure 2. The scheme presented in Figure 2 proves that the navigation system remains operational even if three measuring devices are followed. It should be noted that these devices must be arranged on different measuring axes. Since the fault of two measuring devices which are arranged on the same measuring axis can appear in the losses of operability of the orthogonal redundant system of navigation instruments. Therefore, the approach to the creation of redundant measuring frame with non-orthogonal sensitivity axis is proposed. There are some approaches to location of this measuring non-orthogonal axis of separate sensors. One, the application of the cone as a symmetry figure and the arrangement of the sensitivity axis of navigation devices along generators of the cone. Two, the application of a cone and arrangement of navigation devices at the cone's generators and symmetry axis. And the third approach, arrangement of navigation devices on the facets of the regular polyhedra. The current stage of development of navigation system is characterized by significant complication and expansion of the corresponding functional capabilities. Design of such system requires to increase accuracy and reduce mass and dimensions simultaneously. In this case, it's necessary to satisfy the conflicting requirements. One of the most important requirements for sensors of navigation parameters is a significant increase in reliability. Modern navigation information sensors are perfectly reliable, but increasing the requirements for the reliability of systems as a whole requires using such methods of increasing reliability as redundancy. Usually, in this case, it's possible to continuously receive navigation information in case of failure of some individual sensors, which is extremely important for ensuring reliable navigation of moving objects. It's most expedient to solve the above-mentioned problem using a non-orthogonal arrangement of such sensors. Then we get an increased redundancy of the projections of the vector of the measured parameter on the axis of the navigation system of coordinates, which ensures a reduction in mass and dimensions compared to the use of redundant orthogonal systems for measuring navigation information. So this approach has obvious advantages, but at the same time, navigation information processing algorithms are significantly complicated. The transition from the navigation reference frame to the non-orthogonal measuring reference frame and vice versa can be described by matrix transformations. Here, it's necessary to take into consideration vector of measurements in the non-orthogonal measuring reference frame. Dimension of the measured vector is coincided with the quantity of the sensors. Omega is the measured vector of kinematic parameter in the navigation reference frame, and H is the matrix of transformation between navigation and measuring reference frame. Dimension of the matrix is n by 3, where s in quantity of this sensor. It's necessary to mention that for orthogonal reference frame, such matrix have dimension 3 by 3 only, so we have complication of transformations. Information processing algorithms can be chosen differently. For example, the median algorithm, the weighted average algorithm, or the combined algorithm. But the problem of determining the most accurate readings of the sensor remains relevant in all cases. The modern approach to processing information in non-orthogonal measuring instruments lies in using neural networks. The main components of the non-orthogonal inertial measuring instrument are triaxial MEMS sensors. The non-orthogonal arrangement of measuring axes is achieved by the perpendicular location relative to the polyhedron faces. The tetragonal pyramid represents half of the polyhedron. It's more convenient from the point of view of engineering realization. Since to obtain information about the angular rates of the moving wiggle, it's necessary to process information which enters from 5 triaxial MEMS sensors. This situation corresponds to 15 sensitivity axes. The mathematical description of the triaxial MEMS ray gyroscope can be represented in the following form. Here we take into consideration zero signals, transfer constants, increase of the temperature, and coefficients. The neural network of the triaxial MEMS ray gyroscope is represented in this slide. The more complicated neural network is presented in following slide. It provides information processing in the redundant non-orthogonal measuring instrument consisting of 5 triaxial MEMS ray gyroscope and the constructive element in the form of the tetragonal pyramid. The advantage of the proposed approach are explained by the exclusion of the necessity to use the complex matrix transformations between navigation and measuring reference frame. This approach is especially useful for measuring instruments consisting of triaxial MEMS gyroscopes, as their quantity is sufficiently large, 15 sensors, and corresponding transformation matrices of dimension 15 by 15 in the state of studied case. And you can see this neural network, more complicated neural network. For many senses. Measuring channel of error is described by the relationship 1. Here we take into consideration measuring error, angle protection, and some reference value. The decision making about the measuring channel looks like delta less epsilon. The relationship 1 can be transposed in the form 3, and the expression 2 can be represented as two linear functions. The neural network's first layer carries out functions of assessment of the measurement results, deviations from the possible estimated values. Furthermore, the first layer of this neural network normalizes measuring estimates by sigma function. The effectiveness of the proposed approach to determine the proper function measuring channel can be proved by the modeling results shown in next slide. Perhaps it will be I show the next slide and will explain the previous slide. Figures ABC represent the input signals in the form of normalized signs, which enter separate triaxial measuring units based on MEMS rate gyroscopes. To ensure correspondence of the measuring process to operating condition sensors, outputs are supplemented with a random noise of the definite amplitude. To check the algorithm, it's necessary to believe that one of sensors is failed for some time. The transformation matrix is created using the matrix of weighting coefficients. Further, the transformation matrix is applied for forming output signals. Consider the situation where the weighting coefficients are not implemented. Then the output signal of the non-orthogonal inertial measuring instrument PGG is formed as a mean value of the output signals of separate MEMS rate gyroscopes. It's distorted relative to the representation in Fig H. The represented redundant instrument with the proposed neural network realizes the quorum element. The first layer of the neural network implements information about deviation of the gyroscope measurements from the weighted average value. Figures DE. Weighting coefficients are formed by the second layer of the neural network, figure F. The transformation matrix is created by the weighting coefficients of sensors. And conclusion. The neural network based on learning samples considers this approach ensures decreasing the measurement in comparison with the calculated procedures based on standard information processing methods, for example, the least squares methods. The modeling results, which prove the efficiency of the represented neural network, are shown. The proposed neural network ensures a current analysis of the accuracy of the measuring channels and a generalized estimate of the performance of the initial redundant non-orthogonal measuring instrument. The process of searching for failures is considered. Thanks for your attention.
Thank you for your report. Dear colleagues, do you have any questions? Okay.
I have a question. May?
Yes, Tatiana, будь ласка. You're welcome.
I am glad to see you, but I have not light, but nothing. I have a question about neural network and learning of this source sensor.
This neural network consists of 3 layers: input, output, and
time of completed initial delay.
Back forward. The type of learning with the teacher. And as teacher, we can see the signals of special stand, special bench location. In this case, weighting coefficients of the neural network are corrected by the measurements, by the method of backward propagation of error.
Okay.
Yes, understood. With teacher, but teacher initial date standalone date from simulator, using simulator, no, initial date for what, where you, how you.
No, there are no initial data. All this sensor is mounted at the special bench, which is able to move in 3 directions in the space. So
No.
we
It means
results of measurements, and this is material for learning.
no. It means that you used this neural network, and you studied. You used a teacher for this neural network, and used some previous base of information. Where did you take this initial part for studying your neural network? Tatiana, am I correct? We cannot hear you. Tatiana, please turn on your microphone. Uh-huh. Yes.
Thank you. Yes. 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 No.
Okay, connection is very slow, and we almost did not hear you, but I understand the question. So Olga, please tell us, where did you take the initial data for learning your neural network?
From results of calibration.
Okay, thank you very much. Ivan Astromov, do you have question? I saw that you raised the hand.
Oh, okay, I just would like to ask, what is the level of redundancy is the most efficient, or how many sensors could you propose to use? Two times redundancy or 3 times redundancy? How many sensors gives the best
At
result?
this example, we use 15 sensors instead 3 sensors. Redundancy is in 5 times.
Okay, thank you.
Okay, I see that we don't have other questions. Thank you very much for your report. This report is state-of-the-art topic because in our time of war, we have problem with aircraft navigation using satellites because of special systems of our enemy. That's why this navigation inertial is very important. So thank you for your report. And the next one is report the reference frame based on arch lengths of nonlinear function for smart navigation systems. Okay. Ola, please turn off your slides. Okay.
Okay, hello everyone. Could you see my screen?
Yes, it's okay. Please start.
Okay, okay, thank you very much. That's why my name is Ivan Astromov. I'm from National Aviation University, and I'm a part of Air Navigation team. And today we would like to present you our results in navigation, and especially about reference frame based on arc length of nonlinear function for smart navigation systems. First of all, let me tell you a few words about navigation. Actually, navigation, we means is a positioning and guidance process, because to know movement, to know the way of your movement, first of all, we need to detect where we are. That's why we need to detect our coordinates or measure it with a special positioning sensor. And then we apply some guidance process to direct from one point to another. That's why navigation, it is a process of movement from one point to another, which will continue sequentially until we reach our final destination. And first of all, we need to talk about reference frame, because any navigation task should be solved within some reference frame. And reference frame specify a special relation for both processes, navigation and guidance. And in most cases, we use orthogonal reference frame because it is like a linear metric which help us to count our location and also to detect the way in which we need to move from one point to another point. Coordinates are set of distances from reference frame center to object location by different axes. And in navigation task, usually we use three main types of reference frames based on location of viewer. It can be object-oriented, viewer-oriented, or environment-centered reference frame. From other side, based on metric, usually we have three main types of reference frame. It is spherical, which use latitude, longitude, and altitude to represent location on a spherical surface. It can be Cartesian reference frame, which use orthogonal axes, x, y, and z, in which we can easily get relation between coordinates, between distances, angles to get coordinates. And polar reference frame, which is usually can be represented by azimuthal angle and distance to the object, as for example in radar systems, where we got azimuth of object and we have measured distance to this object. Of course, if we have altitude of object, in this case it is cylindrical reference frame, and also in some navigation purpose we can use cylindrical reference frame. In any case, all of this reference frame can be global or local based on a task which we would like to solve. In our particular task in navigation, usually we have ranges from some navigation points. In case of space satellite navigation system, we got navigation satellites, and we measure distances to these satellites to get our position. If we use, for example, distance measuring equipment on the ground, we also measure distances, and then by measured distances, we solve navigation equation, and we get position like x and y coordinate of user location. In many different tasks, we can use different reference frame. In some case, it can be linearly distributed. In some case, it may be cycle distributed. For example, angles, pitch, roll, and yaw of aircraft orientation in space. That's why when we cross 360 degrees, we will come back to the 1, 2, 3, and come back to the beginning of our reference frame. In our task, we try to think, what if we use non-linear function distribution along their linear reference frame? What if we use some specific function which we can apply based on a particular task or particular parameter to get location, for example, aircraft? And the main advantage of that we can transform data processing from sensor level to the navigation task, and in some cases it may be useful. And the most useful in this case, it is arc length of nonlinear function. And we propose to use the following relation between linear and non-linear function. And in this case, by this integral, we just count length of non-linear function from the reference point of Cartesian reference frame. And in some case, it looks like that we have two reference frames. One of them can be linear, like where we've got x-axis and y-axis, and we've got location of some point. And another reference frame, which has the same reference point, can be not linear. For example, distributed or fluctuated like sine or cosine, if we talk about, for example, radio waves. And the question is if we can measure the arc length of this function, yeah, for the same point, the blue one, then we can use this arc length to localize and to solve navigation equation. That's why we can apply transformation function from linear to non-linear reference frame, and based on this function we can find the wave for direct and opposite transformation. For example, if we have sine or cosine, it will be one formulas for transformation. If it will be circular form, it can be another one, as an example. And if we represent horizontal frame in linear scale of non-linear function, it looks like this one for sine and cosine, because sine and cosine will be in maximum like in some period. However, if you talk about radio waves propagation, we can consider like a dipole vibrator, which generates radio waves, and radio waves is distributed omnidirectional in the following form. That's why we can use different models of counting wavelengths of this radio wave from antenna system center. And then we can, if we can count wavelengths, then we can apply formulas for transformation from non-linear to linear system, and then solve navigation equation. This is like another approach to solving navigation equation. And for numerical demonstration, unfortunately now we do not have traffic. However, we've got a pre-recorded database of air traffic, which we obtained by automatic dependent surveillance broadcast, according to which on board of each aircraft we have a specific transponder which transmits digital signal with location of aircraft. And then we can use this pre-recorded data for simulation of real traffic. And in this case, we use flight RI-55, which was performed 28 December of 1 year ago, 2021, for connection between Borispil Airport and Odessa Airport. And in this case, we transform coordinates from latitude, longitude, and altitude to their local reference frame, northeast up reference frame, related to distance measuring equipment in Kirovograd. That's why during this flight, aircraft is in touch with Kirovograd ground DME equipment for measuring distance. That's why with the help of this beacon, aircraft know exact distance at each point of this trajectory. And we apply our transformation to nonlinear reference frame, also with a reference point in Kirovograd DME ground station. Also, it should be noted that in this case, x-axis is directed to the north, y-axis directed to the east, and z-axis directed up in this case. However, in these pictures, we do not have upscale. That's why we apply in linear reference frame and in non-linear reference frame. And then we count just difference between both of these non-linear reference frame. And here you can see representation, okay, like simulation of distance measuring in different reference frames. That's all for today. I hope when we will have real air traffic, we can measure real data, and we can apply and solve navigation equation in the non-linear reference frame. That's why thank you for attention. If you have any questions, I will be glad to answer.
Okay, thank you very much for your report. And dear colleagues, do you have questions? Anyone? Okay, then I will ask. Okay, Ivan, please tell us about the reason. Why did you need to come to nonlinear coordinates? And what have you what advantages you got from this using nonlinear coordinates?
The main idea to make a simplification of solution of navigation equation. That's why in a typical situation, we measure parameter, for example, distance. We can use, okay, we measure distance for some reference point. And to measure, but actually we do not sense distance. We measure, for example, time traveling. We measure path loss of radio waves. And then by these parameters, we obtain distance, and then we apply multiple distances to get solution of navigation equation. If we jump from linear to nonlinear, we can use exactly measurements in navigation equation. For example, we measure the power of radio transmission. Okay, if it just jump from air navigation to Wi-Fi, for example, we can measure power of Wi-Fi signal, yeah, and we know path loss model in free space, and then by this model we can obtain the distance. The reason to jump from linear to non-linear to using the power of path loss in the navigation equation directly. That's why in this case we just try to simplify a little bit computation performance, because we just once find the first derivatives and create a navigation equation. That's why we do not need to add additional step, transformation from path loss to the distance and then to the coordinates. In this case, we've got a little bit maybe complicated navigation equation. However, we just measure and put results in navigation equation and we got position. That's why the reason to simplify the process of getting position of aircraft or maybe mobile phone in the network.
Okay, thank you very much. It comes a little bit clear. Any other questions do we have? Okay, thank you very much.
Okay, thank you.
Yes, the next report is